what I have written up here is the general process that we came up with a few videos ago of going from code to the runtime of that code for a recursive function. So that intermediate step that we had was finding the recurrence relation for that code before we solved the recurrence relation to get the overall runtime. So in this video, we're going to cover this step right here, going from the code to the recurrence relation. And so what I have here is the code that we came up with in the last video, except again, like with factorial, I've made the steps a bit more verbose. I have some more variable assignments just so that it's easier to see the recurrence relation. So what we saw was that we would define this t of n function, t representing, again, the runtime of f on an input of size n, size n. And we saw that t of n equals d plus r plus c, this being the time to divide or to make our input smaller, plus the time to recurse, which was a function of t as well, and the time to combine, or the time to create our final answer after we've solved the same problem here on a smaller input. And so the time to divide here, or the time to split up our input, is going to be right here. That's d right here. We find n minus 1 and we find n minus 2. The time to recurse, or the time to solve the Fibonacci problem on smaller inputs, is going to be this right here. This is going to be our time to recurse, is going to be these two lines right here. And then the time to combine after we finished recursing is going to be right here. We're going to be adding the outputs of our recursive calls. This right here is going to be our C. So let's look at the runtimes line by line. These subtractions are both constant operations, so these are both going to be, or D is going to be O of 1. If we skip R for now, C, the time to combine, is just going to be the time to add two numbers, which is also going to be O of 1. And now, unlike the factorial recurrence relation, where we had just one call to f of n minus 1, here we have two calls. We have a call to f of n minus 1 and also a call to f of n minus 2. And so the time for the recursive calls is just going to be the time to run f on an input of size n minus 1 plus the time to run f on an input of size n minus 2. So if we simplify by adding these two O of 1s, we're going to get t of n minus 1 plus t n minus 2 plus O1. And so one more thing to notice is that this is only applicable if n is greater than 2. Right? And if n equals 1 or n equals 2, none of these lines are going to get run, and we're just going to run this line, which is also returning 1, which is a constant operation. T of n equals just O of 1 if n equals 1 or 2. So putting that all together, T of n equals T of n minus 1. I'm just copying what I have written here, what I have written here, t of n minus 1 plus t of n minus 2 plus O1 if n is greater than 2, and it equals O1 if n equals 1 or 2. So that right there is our recurrence relation.